Hi guys, welcome back to ChemOrgChem. We have been exploring the name reaction involving organometallics. So in this series, we have already discussed TSUJI-TROST ALLYLATION reaction or TSUJI-TROST reaction in our previous session. So if anyone missed that video, you can find the link in the description box below. So in this session, we are going to see the solution of practice problems from our previous session. So let's moving to our practice problems one by one. So this is our first practice problem. So here you can see that. So this is the allylic substrate which react with these carbon soft nucleophiles under palladium 0 catalysis. So as per this reaction, the initial step is the generation of pi-allyl palladium complex. So now you can see that. So this is the chiral substrate. So in the top phase having acetate group, therefore our palladium 0 should interact with this alkene by bottom phase. So resulting that the generation of this corresponding pi-allyl palladium cationic complex. So now you can see that palladium species present at the bottom phase. So because here you can see that this allylic substrate has acetate group at top phase. Here they didn't mention any base or anything else, so therefore we can assume that this reaction could be a neutral condition. So therefore this 1,3 dicarbonyl compound, so which readily undergo keto-enol tautomerism, which produce this corresponding enol form. So now this enol form, particularly this carbon, act as a soft carbon nucleophile, so which readily attack this carbon. So why this carbon? So here is less steric when compared to this carbon. Therefore this attack mainly takes place at this carbon, and especially this attacks takes place by top phase, since bottom phase has this palladium species, so which produce this corresponding product. Let's moving to our second practice problem. So this is our second practice problem. So now you can see that. So this is our allyl substrate. So along with here you can see that the same molecule has carbon soft nucleophile. So when we treat palladium 0 under sodium hydride condition, which produce a product. So now here you should see that this acetate part present at the top phase. So therefore our palladium 0 should interact this alkene by bottom phase. So resulting that generation of this corresponding palladium cationic complex. So at the same time sodium hydride so readily take one of the proton from this carbon, so which produce this corresponding enolate ion form. Now we should figure out so this enolate form were going to attack either this center or this center. So for that we can start numbering. So this is the first carbon and second, third, fourth, 5, 6. So if attack happen at this carbon, that may produce 6-membered ring system. Perhaps the attack takes place at this carbon. So now you can count that 1, 2, 3, 4, 5, 6, 7, 8-member ring system. So when compared to the 6-member ring system, 6-member ring system is more favorable. Therefore, so this attack is predominant to produce this corresponding product. So apart from that, here you should note it down. So this palladium species present at the bottom phase. Therefore, this attack should take place by top phase. So resulting that generation of this corresponding product with this respective stereochemistry. Let's moving to our third practice problem. So now you can see that this is a lactone, allylic lactone substrate which react with this carbon soft nucleophile in the presence of palladium tetrakis. So initially, when palladium 0 interact with this allylic substrate, so resulting that cleavage of lactone ring to produce this corresponding pi allyl cationic palladium species. Here you should note that stereochemistry, since here you can see that, so this is act as a leaving part. So the leaving part present at the top phase. So therefore our palladium should interact by bottom phase. So resulting that generation of this corresponding pi allyl palladium cationic complex. Now this active methylene compound acts as a soft nucleophile that readily attack this terminal carbon, so resulting that generation of this corresponding product. Let's moving to the our fourth practice problem. So here you can see that, so this one is a allylic epoxide, so which react with this nucleophile under palladium catalysis. So the epoxide ring system present at the bottom phase, so therefore our palladium catalysis should interact this alkene by top phase, which leads to open up the ring to produce this corresponding palladium pi-allyl cationic complex. So now here you can see that the stereochemistry, so this epoxide ring system present at the bottom phase, therefore after opening the epoxide ring, so this alkoxide ion present at the bottom phase in case of our palladium species takes the top phase. So now which react with this nucleophile. Here some of them may get confusion, which is act as a nucleophile here, either this indole NH or this active methylene carbon. However, so this is more acidic position, so therefore this carbon acts as a soft nucleophile which readily attack particularly this center, since this center is less steric when compared to this center. So therefore this attack takes place particularly this carbon to produce this corresponding product. So here we should note it down the stereochemistry. Since our palladium species occupied at the top phase, therefore our nucleophile should interact this center by bottom phase to produce this respective product. Let's moving to the our fifth practice problem. So now you can see that this substrate react with palladium tetrakis and triethylamine under acetonitrile 70 degrees Celsius. So just like our previous reactions, so once this allylic part interact with our palladium 0 catalysis, which readily generate this corresponding palladium pi-allyl cationic complex. So here they didn't mention any stereochemistry, so therefore we can directly put the structure like this. So now we should think about, so which is going to act as a nucleophile here. So either this NH or this indole NH. So this NH is more reactive when compared to this. So therefore this is going to react with this pi allyl part. So for that we need to start the numbering. So here you can start number 1, 2, 3, 4. If attacks takes place at this carbon, which could produce 4-member ring system, or otherwise if attacks takes place at this carbon, that could produce 6-member ring system. So when compared to the 6 and 4-member ring system, so 4-member ring system is one of the strainest ring system. So therefore the formation of 6-member ring system is facile to produce this respective product. Let's moving to the our sixth practice problem. So this is allylic epoxide under palladium tetrakis condition, acetic acid and THF. So here acetic acid acts as a nucleophile in this reaction. So for this reaction, when you get this type of substrate, you just imagine that so epoxide system present at the top phase. You just imagine, okay? So now our palladium 0 should interact our alkene by bottom phase, so resulting that open up the epoxide ring system to produce this corresponding pi-allyl palladium cationic complex. So now you can see that our palladium species present at the bottom phase now which interact with our acetic acid. Here acetic acid act as a soft nucleophile. So now which readily attack this position, since this position is slightly less steric when compared to this position, and most importantly this attack should take place by top phase since our palladium species present at the bottom phase. So resulting the generation of this product with this respective stereochemistry. So here I should note it down. So this stereochemistry is relative stereochemistry, not a absolute stereochemistry. So let's moving to the our seventh practice problem. So this is one of the complex problem. So here first we need to figure out where is allylic part is present with leaving group under this reaction condition. So here you can see that. So this is the allylic part along with leaving group. For this condition, palladium 0 generated in situ which interact with this alkene by bottom phase, which leads to generation of this respective pi-allyl palladium cationic complex. At the same time, sodium hydride readily takes the proton from this hydroxy group that produce their respective alkoxide ion, so which readily react with trimethyl tin chloride which generate this corresponding intermediate. So now oxygen so readily attack this carbon by top phase, since this oxygen present at the top phase. Apart from that, here you can see that our palladium species present at the bottom phase. Therefore this attack should take place by top phase, so leads to generation of this respective product. So let's moving to the our eighth practice problem. So this is cycloaddition problem. So now you can see that when we use palladium acetate along with suitable ligand which could generate their respective dipole. So here you can see that this dipole is quickly isomerized to produce this respective dipole. So now this dipole readily interact with this alpha beta unsaturated alkene, so which readily undergo cycloaddition to produce this respective product. Let's moving to the our ninth practice problem. So this is the problem. Here you can see that this allylic substrate react with organo-zinc reagent under palladium 0 catalysis. So this organo-zinc reagent act as a hard nucleophile. I hope most of them aware about the mechanism involving with hard nucleophiles. So as per this, the first step of the reaction is mostly similar with soft nucleophiles. So now you can see that. So after the generation of palladium 0 catalysis, which readily interact with this alkene by top phase, since here you can see that our leaving group present at the bottom phase, so which readily generate this corresponding palladium pi-allyl cationic complex. So this organo-zinc reagent so readily undergo transmetallation with this palladium center, and followed by reductive elimination takes place by top phase which leads to generation of this respective product. So let's moving to our 10th practice problem. So this problem also based on hard carbon nucleophile. So as per our first step of the reaction, the generation of pi-allyl palladium cationic complex. So here you can see that here acetate present at the top phase which act as a leaving group. So which readily produce this corresponding palladium pi-allyl cationic complex. So now you can see that palladium species present at the bottom phase. So after the generation of this palladium cationic complex, which readily undergo transmetallation with this organo zinc reagent and followed by reductive elimination also takes place by bottom phase, which leads to generation of this respective product. So let's moving to our final practice problem. So here you can see that. So this is the allylic part present with this leaving group. So when we use palladium zero catalysis, which readily generate their respective pi-allyl palladium complex. So now we should see where our this carbon nucleophile should attack, either this carbon or this carbon. Okay, let's start the numbering. So this is the number 1 position and 2, 3, 4, 5. If this carbon nucleophile attack this center, which produce 5-member ring system. If attack takes place at this site, which could produce 7-member ring system. This carbon nucleophile, which acts as a soft carbon nucleophile that attack this site to produce this respective product. So now this respective product react with sodium iodide, HMBA and heat. So here what happened? Carbocho T-carboxylation takes place. As per this condition, so iodide ion readily attack the methyl carbon, so which leads to generation of their corresponding carboxylate ion. So when we heat, so that readily undergo decarboxylation to produce this respective product. So the name of the reaction is Carpaccio T-carboxylation. So after that, which react with 9-PBN, here hydroboration and followed by oxidative cleavage takes place to produce this corresponding primary alcohol. Now this primary alcohol readily react with chromic acid. So this is the condition of Jones oxidation. So which readily oxidize primary alcohol into carboxylic acid derivative. So which then react with diazomethane, which readily produce their corresponding methyl ester. That's it for our practice problem. I hope this video has helped you to understand all these practice problems are based on TSUJI-TROST ALLYLATION reaction. If you enjoyed this session, just give it a thumbs up and share it with your friends. And finally, thanks for watching. Bye bye.